Algebra 2, Set 102, Sums of Functions and Products of Functions. Okay, we have three equations here, and when we're talking about functions, we can name each of these functions a different name. So we can call the first one h, the second one phi, that's the Greek letter phi, and the third one g. So we can name them h of x equals x plus 3, so that's a function notation, and then function notation for phi is going to be phi of x equals x squared minus 6, and function notation for the third one, g of x equals 2x squared plus 5. So what we're going to do is use these functions and perform certain operations on them. Before we do that, we need to identify the domains. We're just going to pick some arbitrary domains. So the first one is reals, the second one is integers, and the third one will be negative integers. And the domains will come into play in just a little bit. So if we have h of x equals x plus 3 and g of x equals 2x squared plus 5, we can add those two equations, and the sum is going to be, we write it as h of x plus g of x equals, now there's nothing to add to 2x squared, so it's going to be 2x squared. And then the second variable is going to be x. Remember, we can't add 2x squared plus x because they don't have the same power. And then plus 8. So the sum of h plus g of x is 2x squared plus x plus 8. So that is how we write it, is h plus g of x. Now, we are going to look at the domain. It says the domain is all numbers that are common to the original domains. So that's the tricky part. So what we need to do is we need to look at our original domains. So the domain for h of x is the real number. So that's every number possible. The domain of g of x is negative integers. So the only thing that negative integers have in common with real numbers are the negative integers. So our new domain is going to be negative integers. Let's do another example, or do an example that kind of helps us figure that out a little bit more. So we're given h of x is x plus 3, the domain is the reals, phi of x is x squared minus 6, the domain is the integers. Find h plus phi of 2. So before we can do 2, we need to figure out, well, first of all, we can split it up. We can say h plus phi of 2 is the same as h of 2 plus phi of 2. So we need to figure out h of x before we can figure out h of 2. So h of x is x plus 3. So h of 2 is going to be 2 plus 3. Now, before we can do that, we have to check our domain. We have to check our input. Our input is 2. And when we combine these two, we have integers and real numbers. So the one thing in common with both of them is integers. So our new domain is integers. And 2 is an integer, so we can continue. So h of 2 is 2 plus 3, which is 5. Then we can find phi of x. Phi of x is x squared minus 6. Phi of 2 is going to be 2 squared minus 6. Or in other words, phi of 2 is negative 2. Now we add these two together, h of 2 plus phi of 2, which is what we were trying to solve in the first place, and we get 5 plus negative 2, which is 3. Now, there's another way to solve this. In this one, we split them up, but we can just as easily put them together, which is what we'll do in this example. So we're going to do h of x is x plus 3, phi of x is x squared minus 6. We're going to add those two together. We get x squared plus x minus 3. And now we're going to put in 2. So h plus phi of 2, check the domain. The domain is an integer. So we can put in 2 squared plus 2 minus 3. So we get 4 minus 1, or 3. Okay, next example. Given h of x is x plus 3, the domain is reals, and g of x is 2x squared plus 5, the domain is negative integers. Find h plus g of 5. So h of x is x plus 3, g of x is 2x squared plus 5. We are adding these, so we get 2x squared plus x plus 8 for h plus g of x. Now, at this point, we need to stop. Before we put an input in, we need to check our domain. when we look at the reals and the negative integers, the only thing they have in common is negative integers. So our new domain is negative integers. So we have to stop. Once the functions are combined, we have to use the common domain, and the common domain is negative integers. So 5 is not negative, therefore there is no solution to this problem. Now we'll talk about products of functions. So if we have h of x is x plus 3 and g of x is x squared minus 6, when we have our two domains there, we can multiply them together. So h of x times g of x gives us x plus 3 times x squared minus 6. So h of x times g of x is going to give us x cubed minus 6x plus 3x squared minus 18. We can rearrange that so the powers are in descending order. So we get x cubed plus 3x squared minus 6x minus 18. So that's h of x times g of x, and we can also write it as hg of x, which is the common notation. So in this example, find hg of negative 4 if h of x is x plus 3, the domain is reals, and g of x is x squared minus 6, the domain is negative integers. So hg of x is going to be x plus 3 times x squared minus 6. So we get x cubed plus 3x squared minus 6x minus 18. Now we check our domain, hg of negative 4. We have reals and negative integers. What they have in common is negative integers. So negative 4 is an element of negative integers, so we can go on. So plug in negative 4 to the equation, so we get negative 4 cubed plus 3 times negative 4 squared minus 6 times negative 4 minus 18. Negative 4 cubed is negative 64. Negative 4 squared is 16 times 3 is 48. Negative 6 times negative 4 is 24 minus 18. When I put all of that together, I get negative 10. So hg of negative 4 is negative 10. Another example. Find fg of negative 4 if f of x is x plus 3, the domain is the reals, and g of x is x minus 5, the domain is positive integers. Before we go any further, you can kind of look ahead before you do any work. Look at those domains and see if they work out with our input. So we have reals and positive integers. So when the two functions are combined, the domain is going to be positive integers. When we look at our input, which is negative 4, we're not going to be able to solve this problem because fg of negative 4, our input is negative, which is not going to give us a solution. So before we do any work at all, we can say that this problem has no solution.